So one of the big things we're going to focus on here are rates of changes at individual points. It's going to be what our idea of the derivative ends up being. So we want to go ahead and explore this idea of average rate of change as well as an instantaneous rate of change. So the rate of change is just the relationship between two changing quantities. The most famous rate of change is velocity. So the velocity is just a change in position. It could be height, distance. We also could call this displacement. So the change in position is just really the displacement with respect to time. So we're going to already have something changing with respect to some other thing. So other rates of change could be, say, the change in the amount of an infected population you have with respect to time, the change in temperature with respect to altitude, or the change in profit with respect to the units sold. Could be respected with a lot of things, respect to demand, with respect to the hours of work. Could be with a bunch of things. So let's start off with a definition. So we're going to let S of t be a function that measures an object's position. Then the average velocity of the object over the time interval t1 to t2 is going to be given by the change in position divided by the change in time. So the way we're going to represent this symbolically is with these delta s and delta t. So change in position divided by the change in time, and this is going to become s of t2 minus s of t1 divided by t2 minus t1. So we've got our two position values, because remember s of t is going to be measuring the position, and the t's are these times that we're looking at for this time interval. So let's go ahead and look at an example. So let's say we wanted to go ahead and compute the average velocity of a stone tossed vertically from the ground with an initial velocity of 15 meters per second over the time interval 0.5 to 2.5, whose height at time t is given by this equation, h of t, which is going to be equal to 15t minus 4.9t squared. So note that, just to be clear, we're using the position this time as h instead of s, but we know what our position function is. So our average velocity is going to be our change in height over our change in time. And since we're looking between 0.5 and 2.5, we'll find this by taking h of 2.5 minus h of 0.5 divided by 2.5 minus 0.5. And so when we do this, we will get 15 times 2.5 minus 4.9 times 2.5 squared minus, it's important to make sure we put this part in parentheses, 15 times 0.5 minus 4.9 times 0.5 squared. This will all be divided by 2, because that's 2.5 minus 0.5. So we want to go ahead and make sure we keep in mind checking how we put things in the calculator. So just so for this first time for some practice, we want to take 15 times 2.5 minus 4.9 times 2.5 squared minus, in parentheses, 15 times 0.5 minus 4.9 times 0.5 squared, not log, squared, parentheses. We need to put another set of parentheses again. So this first set of parentheses are these square brackets here, and this other set of parentheses is giving us our entire numerator. So we want to divide the entire thing by 2. So we put this in our calculator. We should get a value of 0.3, provided that I type things into my calculator correctly. Now let's talk about our units for a second. What we're doing here is we're taking our height, which we said was in meters, and our time, which of course is going to be in seconds, and we're dividing those. So essentially we have 0.3 meters per second. Okay, so what if we wanted to go ahead and find the velocity of an object at one specific moment in a time interval, say sometime t naught, as opposed to over a whole interval? So instead of us having 2 times and us wanting to get the average, what if we just wanted to look at one specific point? So I want to find the average velocity at t naught, or in other words, the interval t naught to t naught. Well, this would give us then s of t naught minus s of t naught over t naught minus t naught, which would be 0 over 0. Well, that's undefined. So we can't do that. So we're going to have to try to do something else. So what we're going to do is we're going to find average rates of change of s of t over smaller and smaller intervals that have this t naught, and try to use that to get close to that specific moment. So note that the average velocity is going to converge to, in this case becomes, the instantaneous velocity. As we're shrinking our time interval closer to 0. So instead of trying to think about, going from, say we wanted it at 1 second, we want to look at the interval from, say, 1 second to 0.00001 seconds. So we'll be taking and trying to get a small interval around it. So let's go ahead then and try to estimate the instantaneous velocity of the stone from this first example at time t equals 1. So let's get that over here. So we've got them both together. Okay, so we